All right, so we are taking a look at section 4.4 today, and that is talking about graphs of logarithmic functions, all right? And so in many ways, this is a review of stuff that we did with 4.2, okay? So this should be very similar to 4.2. And all the WebAssign from this past week. And it's all about graph transformations, okay? We're just looking at a new graph. And so I think that we can take this, what we know, as a good place to start, all right? And so what we know is that we've looked at this exponential function. And if we have certain letters in certain places, then we can actually tell based on where those numbers are, how they move our graph, right? And so this would be our graph transformations, okay? Now, most of us on quiz 2 did a great job in terms of thinking about the order in which the graph transformations happen. But there were a few of us who I think either forgot that there was an order or didn't realize that there was an order. And so I want to make sure that we're aware that there's a certain order in which these graph transformations happen. And so the question that we sort of asked ourselves was like, if we have a number for X, like which of these letters do we do first, right? If we plug in a number for X, what is the first uppercase letter that we would use on our X value?
C.
Yeah, we would use C, right? And so I kind of did these in like a rainbow order situation. So the first one we have right here is that we have that C value. And what does that C value tell us? Like, let's say I had X plus 5. What would that plus 5 tell us?
It's going to move 5 units to the left.
Perfect, perfect, right? So if we see a plus C, that means we move it to the left. And if we have a minus C, that means we move the function to the right, okay? All right, after B, or after C, we go to B, right? What does that B value tell us?
The B can stretch or compress the horizontal part.
Ah, yes. Good, good. All right. So I see that Dallas has put in here that's a stretch or compress. I agree with that. We want to be a little bit more specific in that this is a horizontal stretch. Or compression. And if we wanted to be even more specific, we might even say that the compression happens when B is greater than 1, but it stretches when B is between 0 and 1. Right. You'll notice that I like to revisit these concepts a lot. I think that's so important because one of the things that we don't actually get in a sort of accelerated college class is sometimes we learn one thing one day and literally we move on the next day and that's it. Right. And it can feel very overwhelming if you're like, I just didn't understand that. And so it's really important that we at least see it as many times as we can, but also that we sort of ask if we are not sure about something. Okay. All right, what comes next? After C, after B, which transformation do we look at next? Yeah, we're gonna move to A. And what does A tell us?
If it's a vertical stretch or compression.
You got it. Vertical stretch or compression. And are these going to be the same as with A, or are they going to be different?
They are different.
Yeah, they're going to be the opposite of B, actually. Okay. And so for our A, our A value is bigger than 1, we're going to get a stretch. And if we have our A value between 0 and 1, we're going to get a compression. Okay. And we have one last letter here. And what does that uppercase D tell us?
If it moves up or down.
You got it. And in fact, if we have a plus D, we will shift the function up. And if we have a minus D, we will shift the function down. Okay. And so for those of us who were feeling a little unsure about these, I hope this was a good little review, but we're going to get a chance to practice this with a new function. Okay. So this structure right here, it works for every single function that we're going to look at. The question, though, is really, what does this part with the graph transformations look like? Okay. And so let's sort of move on over to what's new. And you'll notice here that we don't have an exponential function, but rather we have a log function. Okay. Now, I do want to ask a question, which I think if you watched the rest of the 4.3 video, you may know the answer to, but if you did not, you may not know this answer. So here's my question to you. Is log x a common log or a natural log? And how do we know? All right, so I see one vote in there for a common log, and I'm wondering what our clue is. Like, what clue tells us that it will be a common log? And good. Okay. So one of the things that is actually super important to like our general success is that we have a shared vocabulary. And so it's important for us to be able to say, okay, a common log, just like Dallas has said, a common log has base 10. Okay. Whereas a natural log, what does the natural log have a base of? Base E, exactly. Okay, so in this case, we're looking at a common log, all right? And it's one of those situations where, like, a lot of times mathematicians, they'll just be really lazy. They'll leave out numbers and expect you to just know what they are. And so you'll look at this and be like, I don't see a base at all. Well, it turns out that that base is a 10. All right. And because most, not all of us, but most of us, I think, have 10 fingers, 10 toes. We count by tens, right? We go like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we sort of start over again, 11 all the way to 20. And then we start again. And because we use this 10 so much, we call it a common log. Okay. But my question for us is, how do we write something like this, but with a log function? Okay. And so that's what we're going to do right now. So we can say our graph transformations, we're going to have f of x. And just like we had over in the exponential one, we're going to start with an uppercase A. All right, that's the first thing that we write, but it's the third thing that we actually do in our graph transformation. Now, I don't want to write an exponential here. I'm going to write the log part. I'm going to open up a set of parentheses, and we're going to have b parentheses x minus c. And I got to close it because I opened two parentheses, so I have to close two of them, and then plus d. All right. And when we look at these side by side, as mathematicians, we should notice that some of these things are very similar, right? If we look at this log graph transformation one, if I put in a number for x, the first thing I'm going to do is still going to be the c value. And the second thing I'm going to apply is the b value. And the third thing I'm going to apply is the a value. And just like with the exponential, the last thing we're going to apply is the d. Okay. And so this, just like we had over there, is still our graph transformation. Okay. Now, that part's the same, but what's different is we're going to have a different shaped graph. All right. What is one feature that we know about the graph of the log function?
Can you repeat the question? I couldn't hear.
For sure. What is one feature about the log function? It could be the shape of it. It could be, does it have an asymptote? It could be, is there a center point? Yeah, we do have a center point at 1, 0. And so in fact, that's going to land us right about there. All right, what other features does a log function have?
Did it have a vertical asymptote?
It does, sure does. And so that's something that we want to make sure that we draw in. We've got this vertical asymptote. I think we had chosen a different color. We've got our vertical asymptote here. And what would the equation of this vertical asymptote be?
X equals 0.
Yes. Someone tell me, why is it not y equals 0?
Because it's on the x-axis. Oh, no, because it's on the, because all the points there are equal to 0 for x.
Good. All points on this line have x value of 0. Perfect. All right. Now the shape of this function is not like this, right? Because if I drew something like this, that would be an exponential function. But rather, we sort of start down pretty close to that vertical asymptote. We come up, we go through our center point, and then we sort of continue to go up, but it starts to grow more slowly. Okay, it starts to grow more slowly. And so when we're thinking about sketching our log graph, this is about as much detail as I'm really looking for. I don't need you to sit and plot every single little point because we end up with a lot of decimals with these. And so the nicest point happens to be that center point, okay? I think it is also helpful to consider that vertical asymptote and like where it is, because that might be helpful in thinking about when we move things side to side, okay? All right. I do want to do this log base 2 real quick. We did this last week when we first started learning about logs, but I think there's a lot of process here that I just want to make sure we're doing really good with, okay? And one thing that I want us to note is that when we're choosing our X values, we really want to think carefully about which X values are going to be best for this function. And so in general, we might think, oh, I start with like 1 somewhere. But when we're thinking about the logs, we almost want to think, how can we get some nice Y values out so we can plot them and it's not a whole bunch of decimals, okay? And so we in fact pick 2, we don't pick 3, but we pick 4. Anybody think of another nice number that maybe I could plug in over here? Yeah, we
8.
try 8, good. All right, and then what about these values? Are those going to be like -2, -4, -8? What might we want to choose there? Nice, yeah. I think 1/2 would be a real good one. And if we follow in that same pattern, exactly, we maybe choose, whoops, 1/2, 1/4, 1/8, okay? Now, this is something that maybe some of us sort of knew walking in, or we've seen it once and we're like, oh yeah, that makes sense. But I think there's a beauty to making sure we know how to choose nice points. And it's an area that I would like us to sort of grow in over this year, okay? All right, so if we do plugging in all our values here, when I plug 1 in for X, I end up with 0, okay? In fact, this is log base 2 of 1. Let me write it down here. Okay. If I go through and plug in all of the X values, log base 2 of 2, log base 2 of 4, log base 2 of 8, all right. This question, log base 2 of 8, what is that really asking me?
2 to the power of what is equal to 8?
Exactly. Log base 2 of 8 is really asking us 2 to what power equals 8. Okay. And when we ask it like that to ourselves, I think we know that 2 to the 3rd power is 8. Okay. Over here, we would say 2 to what power gives us 4? And we would say 2 squared is 4. And then we'd say 2 to what power gives us 2? We'd be like, oh, just the 1st power. Then this is where we really want to make sure we know our fractions and our exponent rules. 2 to what power gives us 1/2? 2 to what power gives us 1/4? And 2 to what power gives us 1/8? Right. And if we were to plot all of these points, we would find they get really close to this line right here, but they don't actually cross it. And if we plotted all of these, we would get our 0, 1, our 2, 1, our 4, 2, our 8, 3, our 1/2, -1, 1/4, -2, and 1/8, -3. They get like super, super close there. And then we could connect them all. We'll see that this top part, sort of, it continues to go up, but it grows more slowly than like this beginning part where things are going up pretty quickly. Okay. In fact, I would say this is sort of what I hope your experience is like in this class, that maybe in the beginning you're like, whoa, there's so much to learn. But as we kind of repeat things and see the same structures again, that you'll be like, okay, I'm sort of getting the hang of it. And not that it's going to be easy cruising. We're still going to be continuing to work hard, but I think this onboarding part, right? The first 2 weeks, figuring out how to redo your schedule, all of that, definitely a lot. But as we sort of get into the swing of the semester, maybe it starts to feel a little bit less intense, okay? I do want to write a note for ourselves here that this end does not flatten out. It still keeps growing. Okay. All right. Let's go ahead and move on. All right. So in general, when we're sketching, things that I'm looking for, and we kind of talked about this earlier, I don't want to say x-intercept. We're going to give that the same name we said before. We're going to call that the center point. I would like you to keep track of that center point. The general shape of the function, so thinking that we have something kind of like this. And then where is that vertical asymptote? So you should have a vertical asymptote, and the equation will always be x equals some number. Okay. All right, this chart and space should look really similar to what we had for our exponential ones. But again, I think that the more we write things, the more we hear things, the stickier that becomes for us. And so if we think about this graph transformation, we have our A log B parentheses x minus C plus D, right? That's all the same as what we wrote before, but now we're thinking about it in a specific order, right? And I want to add a little bit too, as we start to pick up on some patterns, I think it might be valuable, all right? So we'll start with our C and then our B, and then our A, and then our D. Right? And earlier we said that if we have C, that takes care of a horizontal shift. Okay. And we also said that B took care of a horizontal stretch or compression. Let's go back up and look at what we wrote earlier. Okay, so we'll come back down to this screen, but I want to sort of scroll back up to the very beginning real quick. And in particular, if we look at this one over here, right? One thing that folks might have realized is that all the things that are horizontal are sort of the opposite of what you think they might be. And what do I mean by that? Well, if I have x minus C, we usually think about minus being in like the negative direction, right? But if we have a minus C, that actually moves it to the right, not to the left. So that might be tricky for us to remember because it's backwards or the opposite of what we think. And similarly, if we look at B, we might think that a stretch would be greater than 1 and a compression would be less than 1, but with the horizontal situation, it's actually the opposite of what we think. Okay. What would you say about the vertical ones? Do you think those are exactly what you think they should be, or do you think they are the opposite of what you think? Yeah, the vertical ones tend to be exactly what you think they should be. And it is the horizontal ones that are actually the opposite of what we think they might be. Okay. And so that's the piece that I'd like to add to the notes that we have down below. All right. So not just thinking, oh, C is a horizontal shift and B is a horizontal stretch or compression, but leaving space for ourselves to think that this is going to be the opposite of what we think. Okay. But then when we get to the vertical, the A, which is our vertical stretch or compression, and our D, which is our vertical shift. It's almost like we're in the home stretch. These last two transformations that we think of are exactly what we think. Okay. All that means is when we look at things that are happening horizontally, we need to be a little bit more careful. We don't want to rush through that. We want to think, okay, this is the one that is the opposite of what we think. But once we get to the blue and the green, like the A and the D, then we're thinking, now we're in the home stretch. If we see a plus, it means up. If we see a minus, it means down. If we see a greater than 1A, it's going to be a stretch. If we see a less than 1A, it will be a compression. Okay. There's also one last note I want to leave for ourselves. What if we have a negative B? What does that do to our graph?
It flips it on the y-axis.
Mm-hmm. So, yep, we say it's a reflection over the y-axis. And the reason why I'm putting that in quotes is because it's like after we've moved it, now we flip it over where that new center is. Okay. And then what if we have a negative A? What does that do?
A reflection on the x-axis.
Good. Reflection over the x-axis. All right. And so if these feel pretty familiar to you at this point, that is excellent. All right. That means that you've done a really good job with the onboarding of the last week, that you've put in the time and effort, and that you've been exploring all those really cool resources that folks posted in that 15C discussion. All right. And if all of this is still feeling really like a lot for you, I would encourage you to go to the 15C, look at some of those video resources or some of the non-video resources that folks have shared to help you unpack this a little bit more. Okay. All right, now I know we spent a lot of time thinking about the horizontal like pieces and all of that, but what I'd like to focus on right now is actually just doing some of the questions. So we'll kind of reverse our approach to what we did for the exponential ones, okay? But before I post the notes for today, I will go back in and fill this part out so you'll have it there. But what we're gonna do right now is really think about the examples, okay? Because I think for some of us, we're really good at looking at like new ideas and then applying them to a problem. And I think for other people, it's really helpful if we see an example. So I want to make sure we hit sort of both types of learners here. Okay. All right. So let's take a look at example 2. It says, consider the graph of f of x equals log of x plus 1. And notice that this x plus 1 is in parentheses. Okay. So let's think about what graph transformations happen. All right, so this is actually also really good about thinking about, like, sometimes if I ask you to show your thinking, it's okay to tell me just like what direction the graph is moving. That is one way of showing me your thinking. All right, so what transformation is happening to this graph right here?
It's going to be a C transformation, so a horizontal shift.
Mhm. And we are going, yes, we are going a horizontal shift to the left, okay? So here's an example of how you could write this. You could write that is a horizontal shift left 1. That would be totally fine. Some of us like more words because it's easier to go back and understand what we were writing. Or if you wanted to even just do something like this, like 1 to the left, that's fine too. Okay, so here's an example of one thing you could write when I ask you to describe a graph transformation or show your thinking. This is also a valid way of showing your thinking. Okay. All right. Now, if we move something to the left, do we change our center point? Yeah, we are going to change our center point. And in fact, let me go ahead and sketch a quick graph. All right. Some of us are good at doing this visualization in our heads, and I'm not necessarily one of those people. Like, if I have a picture there, it makes it easier for me to answer the question. That's just something I've learned about myself over the years. And so if I can take 30 seconds and draw a picture, it helps me answer the question better. Okay. So if I take this blue log function and I move it to the left 1, what does my new center point become?
0, 0.
Mhm. Perfect. Because I take this 1, 0, and I literally move it over 1 to the left, 0, 0. Okay. What else changes? Yeah, that asymptote, such a weird word. There's like so many consonants in a row and you don't need to say them all, but an asymptote, right? The asymptote changes. Great. What is the new vertical asymptote?
X equals -1.
Perfect. We're going to take that. We're going to move it to the left as well. Exactly. Okay. And so this would be sufficient to show me your thinking, because it shows me that you were able to think, oh, from the equation and the picture together, like, where does everything go? Right? And everything just moves over to the left one. All right. Let's take a look at example 3. All right. Take a look at that function and let's go through a similar process. What's the transformation? What's the center point? What's the vertical asymptote? Okay. All right, I see a horizontal shift to the right 5. So you could say that. Or you could draw an arrow to the right and write the number 5, and that would be absolutely fine. Okay, so you have choices. You don't have to write out that many words, but you do have to show me a little bit of that thinking. Okay. All right. We can take that same picture. We can imagine we're at 1, but I'm going to move over 5 places. So 1, 2, 3, 4, 5 places, that's going to get me to not 1 0, but 6 0. All right. And same thing, if I take this vertical asymptote and I move it to the right 5 units, 0 plus 5 will give me x equals 5. All right. So not too bad. We're just looking at a single transformation. But you'll notice on some of the quiz questions, I ask you to do like each one sort of step by step. This would be the first one that you try and do, right? Anytime you look for any horizontal translations, that would be the first one that you draw. After you do that, then you're looking for any horizontal stretches or compressions. And that's what we'll take a look at in the next example, okay? So again, I will go back in. I will fill this part out before I post the notes for today. All right, but we're going to focus more on the examples because I think those are more like the quizzes and maybe will help us feel like we can actually do the quiz questions. Okay. All right. So we're going to take a look at this. Consider the graph of f of x equals log of 3x plus 6. And let's think about what is changing. All right. Now, with something like this, one thing that I do want us to be really thoughtful about, and if you attended Yitan's tutoring sessions, he may or may not have brought this up, but what's my B value here?
3.
3. Okay, what's my C as in cat? What's my C value?
Would it be 2?
It is not 6. Okay, it is not 6. So I do want to say, if we look at this, capital B does equal 3, but I'm going to write this in red. Capital C is not 6. We'll put a red frowny face there because that, my friends, is the #1 mistake here. Okay. So when I ask, like, show me your thinking, this next step would be really important. All right. And the next step is this. We're going to factor out a B. 3 times x plus what gives us 3x plus 6. Now we get that plus 2. Okay, so what did we do here? We factored out the B. Okay. How important does that look? It looks so important. Who thinks I'm going to ask a question like this on the test? I hope the answer is everyone. Okay. I want us to, this is the #1 mistake, and I don't want us to make that mistake. Okay. This is my B. That's all fine and good. But this number is not my C. I have to factor out the B in order to find the C value. Okay. So we do still have our B equals 3, but in our happy hot pink color here, we can say that C is that -2. Okay. Whoops. Now that we've done that setup, now we can talk about what transformations are happening. Okay. And in particular, this function is going to move to the left 2, or you could say a horizontal shift left 2. Okay. But then something else happens after that. What is that something else? In fact, what does that B equals 3 tell us? Mhm. So we could say horizontal compression of 3. Mhm. All right. Those are the graph transformations. Can someone tell me where our new center point is? And where our new vertical asymptote is? You might have to go back and look at that picture, the one of the logarithmic function that we drew above. Did you mean to put a 5 in there?
Yes.
Where are you getting the 5 from here?
Oh, yep. Now,
Okay. What might we want to change that 5 to, or -5? Mhm. The center point was at 1, 0. We move it 2 places to the left. We get -1, 0. Right. Our vertical asymptote was at x equals 0. So when we shift 2 units to the left, what is the new vertical asymptote? Yep. Perfect. Okay. Let's try one more like this, all right? Because again, I think this is the trickiest one to make sure that we get correct. F of x is log of, oh man, I even put fractions in this. Okay. My b value is 1/2. My c is not -8. I'll give you a moment. And I'd like you to, in the privacy of your own learning environment, factor out b, and then send me a message that tells me what you think. All right, so I'd like for everyone to do this. Right, so in the privacy of your own learning environment, you're going to go ahead and factor out that b value. And then all you're going to type in is what number you think c is, but you're going to send that to me directly. Okay, not to the whole chat, but to me directly. Right, this is good. I've heard from a few of you. I'm waiting for more of you. You are all important. All right, right or wrong, it is important for me to know where we're at as a class, okay? All right, I'll give folks another 30 seconds. All right. This is good. This is good. Okay. So we have answers in sort of two different camps. Some people put a 4 here. And some people put a 16. Who's right? 4 or 16? Those were our top two answers.
I will say I'm a part of the 16 group, and I believe it's 16 because you have to reverse the 1/2 out of it. So you have to divide by 1/2, which is the same as multiplying by 2.
Yeah, if you're not sure, and let's say you put in a 4 here, right? Before you commit to that answer, I would just distribute that 1/2 back in for yourself, right? If I do 1/2 times x, I get 1/2 x. But if I do 1/2 times 4, I don't get 2. I actually get, or I don't get 8. I actually get 2, right? So if you're not sure, just do yourself a favor and just like distribute it back in and see if you can get the answer you started with. But I would say for those of you who are in the 16 camp, you were indeed correct, because 1/2 times 16 gives you that 8. Okay. All right. So what does that tell us? That tells us our B is 1/2 and that our C is 16. Okay. All right. What transformations does that mean? I think this minus 16, it is the opposite of what we think. It means we are moving 16 units to the right. And this B is 1/2. Am I going to have a horizontal stretch or a horizontal compression here? Yeah, we're going to have a horizontal stretch because it is the opposite of what we think. And in fact, we are stretching by 1/2, meaning we're pulling it out twice as long in the horizontal direction. Okay. Now we're moving 1, 16 units. So that's going to give us 17, 0. And we're moving our x equals 0 to be x equals 16. Okay. All right, let me pause here for a moment. Are there any questions on examples 4 or 5 before we move on? All right, well, let's go ahead and move on then. I'm going to take a look at that A value, right? That's what comes next. And again, I'll go ahead and fill this part in at the end of class, but I'd like to focus on these examples that we have right here, okay? All right, so we are layering, right? We're layering, we're adding something new to each of these questions. Some of this we've already done. If we do not rewrite this, then we're going to get the wrong answer, right? We would want to write it as 5 log of 3 parentheses x plus 2, just like we did in the previous question, except now we have this 5 here, right? So we should still have to the left 2. That's still there. We should still have a horizontal compression of 3. But what is the new transformation that we are adding here? We've got a vertical stretch of 5. Okay, so very, very similar to question number 4, except now we've got a vertical stretch of 5. All right. Let's think about our center point, our vertical asymptote. Can answer either question. Pop that into the chat. Let's see what we get. And I'm seeing some good answers in there. All right. I agree that that vertical asymptote is going to be at x equals -2. Okay. Well, let's think about what happens for that center point. So I start with a center point at 1, 0, right? I'm going to move that over 2 units. So I'll be at -1, 0. And then the stretches and compressions don't actually change that. All right. Example 7, super, super similar to example 5, right? We see that 1/2 again in there. When we factor that out, we're going to get that 1/2 as our b value and then x minus 16, right? And so if we go through our transformations, we're going to do the 16. Then we're going to apply the 1/2. Then we're going to apply that 1/6. So we're going to move to the right 16. We saw that before. We're going to have a horizontal stretch of 1/2. And what is our newly added transformation for this? Good. We're going to do a vertical compression of 1/6. Perfect. Okay. And I'll let you kind of play around with what that vertical asymptote might be, what that center point might be. Okay. All right. Let's move along to our last one. We have that uppercase D. All right. And so let's think about what we do or don't need to rewrite here. If we look at this f of x, log of x plus 6 plus 1, what transformations would you tell me are happening? I would agree with that. I would say that +6 means we're moving to the left 6. And again, you could write it as simply as that. And that the second thing that is happening is we are moving that function up 1. Okay. Where's the new center point? And where is that vertical asymptote? Yeah, that center point, we're moving over to the left 6 units. So I agree that's going to turn that 1 into a -5. And then we are moving it up 1. So that's why we get a 1 instead of a 0 there. Great job. Good. And then we're going to take that vertical asymptote. It was at x = 0. And now we're going to shift it all the way over to x = -6. And I do want to say to those folks who are engaging in the chat, I really appreciate that we're being so thoughtful about writing out the entire equation, like x = -6. I think that sometimes we can start to be lazy about our typing and not write that in, but that sort of reinforces the idea that it's not important. But we really want to be really clear in our notation so that anyone looking at our work knows what it is that we are trying to communicate. Okay. All right. We're going to take a look at this last example, but I want to modify this a little bit. Okay. So I'm actually going to change this last example to really drive home a point in terms of like how important the factoring piece is. Okay. So we're going to rewrite this f of x. We're going to say that we have f of x equals log of 8 minus x minus 3. Okay. 8 minus x minus 3. What graph transformations do we think are happening here?
I would say we have B, C, and D.
B, C, and D. Okay. And what do you think those values are? And not you specifically, but sort of the global you, us, all of us together in this class. What might those B, C, and D values be? Yeah, I would agree. This one right here, we're moving down 3 units. Yeah. B is -1. Okay, I buy that. I buy that. Okay. Omar, I'm so glad that you put in that C is 8. Don't be sad that I'm writing it in the red. Okay. It's almost like I wanted someone to write that. Okay. I wanted someone to say that. The reason why is because just like the other questions, we need to factor out our B value. Okay. We need to still factor out that B value. So let's go ahead and factor B out. And then let's see what that tells us about the C value, okay? So here's what I mean by that. We could have log, and I'm gonna go ahead and just write like -x plus 8, right? 8 minus x is the same as -x plus 8. But I think when we write it this way, it's more obvious to us that we need to factor the B out. I agree that the B is -1. What's left inside the parentheses when we factor out a -1? Yes, x minus 8. Good, good. Okay. Now, let's modify what Omar put in the chat. I agree that D is at -3, B is -1, but what can we say about C now? In particular, which direction is that? Yeah, C is going to be our 8. We're moving this to the right 8 units, right? This means we go to the right 8 units. But look at what we had before. If C was that +8, we would have moved it to the left 8 units. Right? So by factoring out that negative, we're able to determine the correct direction in which a function is being transformed. Okay, and so that's why I wanted to finish with this last problem here to really drive home the fact that we need to factor out that B. It will mean the difference between going in the correct direction and the incorrect direction. All right. And I know we don't want to make those mistakes. So I want to be really careful about this. And I think I tried to incorporate those into the quiz. So be on the lookout for those on the quiz, because I want us to be prepared for those so we can avoid that number one mistake that folks typically make. Okay. I think we've done a really good job in internalizing what the B and A negative values do. The reflections are still the same. I will write these out again before I post the notes for today, but I think this is a good place to sort of wrap up our 4.4 lecture, okay? So I'm gonna go ahead and stop the recording.